Now, we are going to discuss estimation of design parameters. So, let us take an example and try to understand how we can calculate some of the design parameters when specification of a product is given, especially the performance specification is given. So, let us say here there is an example where the product specification is given like warp tensile strength 98.2 kg force per centimeter. This is the minimum strength that is required. Then web tensile strength also 98.2. So, that means both direction we need similar strength, and that is the bare minimum. If the strength is more than that, it is okay. The GSM is nominal value should be around 0.27 kg per meter square, and the minimum acceptable is 0.24 and the maximum acceptable is 0.31. So, average is 0.27. The environment is acidic, that is pH is 6.0. Structure restriction nil, that means there is no restriction on the type of weave that we are going to use. It could be plain, it could be twill, it could be whatever, that has been left to the designer, that any construction is fine. And then ends and peak densities are also not giving, that also can be decided. The thickness has to be 0.05 centimeter, that is 0.5 mm. So, these are the some basic requirements are stated. We need to find out the relevant design parameters or design variables, which is being shown in the next slide or the present slide as it is. That means, the variables we need to know it what should be my warp count, what should be my weft count, what should be PI, what should be PPI, and what should be the yarn tenacity. These values we have to calculate from the information given about the product specification, which is on the left side table, and we need to find out what should be the design variables, and the other thing also we need to know what should be the fiber also. This is also we need to know which fiber we should choose, which will satisfy these requirements. Okay. So, let us move forward now. When it comes to material selections, what we need, that as a designer you need to put in place some of the fibers which you feel suitable based upon the basic minimum information given. So, here we have a list of polyester, nylon, olefin and glass fibers, and some certain relevant properties we have to dig out this information and we have to put them together, because that is what we need to find out the kind of material that we need. So, if we like the polyester, because it is a acidic medium, we need to know what could be the reaction of polyester to acids and alkalis. So, accordingly we can choose the right fiber. So, polyester resistant to most of the mineral acids, but disintegrates by 96% sulfuric acid. It resistance to cold alkalis and slowly decomposed at boil by strong alkali. Nylon decomposed by strong mineral acids and resistant to weak acids, where with respect to alkali little or no effect. Olefin fibers, polyolefins such as polypropylene, like them, they are very resistant to both acid and alkalis. So, they are that way very suitable, because from damage point of view they are good. Glass fiber resist most of the acids, but attacked by hot weak alkalis and concentrated alkalis, and their relevant densities values are given, moisture regain values are given also, some tenacity values are also stated, and relative strength in wet state also is given. because the fabric is going to be used in the swimming pool, and therefore, we need to know also that the strength should not decline if it is wet, though the fabric will be completely will be covered by some chemicals, that is, but there could be occasions where it may be exposed to the water and the water can penetrate and it can then weak the fibers of the fabric, the tenacity may go down. Therefore, the relative strength in wet state also is important for us to know, and based on this information we have to decide which fiber we should choose. So, the criteria should be minimum moisture absorption, resistance to acidic environment and high strength to weight ratio. So, that the overall weight of the fabric is minimum, and therefore, high strength to weight ratio is always good for us. Now, see the moment it comes high strength to weight ratio, the glass is very heavy, 2.5 is the density, though it has a very high tenacity, but density wise very high, and therefore, glass fabric will be very heavy for this particular purpose. So, we have to discard glass. So, like that, if we go to olefin fibers, the tenacity is on the lower side, and therefore, we have to discard this, though otherwise it was okay, moisture regain is 0, no change in strength when it is wet. So, we are left with two fibers now, polyester and nylon, both are good in some respect, and but if we see the resistance wise, the acidic environment will suggest that polyester will be the best and it should be the first choice, then followed by nylon. So, we can choose polyester and also nylon, but preference will be given to polyester, because polyester is also cheaper than generally nylon fibers. So, therefore, we should go for polyester fiber. So, that is the material selection part. Now comes the other parameters, that is, we need to know what should be the tenacity of the yarn and what should be the yarn count and what should be the EPI and PPI. So, warp strength has been given in terms of kg force per centimeter, that is 98.2 kg force per centimeter, which is equivalent to 249.43, that is almost 250 kg force per inch. So, this is the value which has been given and we have to meet this requirement. So, let us EPI stands for ends per inch, PPI stands for pegs per inch, and WPTX is the linear density of the warp yarn. Similarly, WF TX is the linear density of the weft yarn, TWP is the tenacity of warp yarn, and then we are writing what should be the tensile strength of the fabric, and we can write that the tensile strength per inch of the fabric is going to be EPI, that is ends per inch, into WPTX, whatever is the warp count, into tenacity of the warp divided by 1000, because we have to convert it into kg. And there is a eta here, it is the translation efficiency of yarn strength to fabric strength, and this value depends upon the cover factor and fabric weave. So, this is the value we need to assume. We have assumed a value 0.96, and now how do I assume certain values? For that we have to actually search certain literatures, we have to consult some books. So, whenever certain parameters are not given, we have to make some assumptions, and while making some assumption, it should not be completely arbitrary in nature. We have to consult certain research papers which are there, or some textbooks, and we have to find out what sort of values people have reported. And a typical value we have to assume, so that we can make some estimation of the parameters to start with. It is basically the first iteration. So, we assume a value 0.96 and then we write the equation number 1, where this is the strength given, and on the right hand side you see we write 0.96 EPI WP TX TWP by 1000. So, that becomes one equations. Similarly, for webbed tensile strength we can write similar equation exactly, because here both way we need the same strength. Next, this is what is important now, because the previous one, if we look at this, we will not be able to really, we have two equations, but there are three unknowns. So, there is no way to find out the values of these parameters, since we do not have sufficient information is not there. So, now let us go to this page. What it is stated here? Now, another information which has been given is the fabric areal density. Now, we know that the areal density of a fabric can be written as 1 by 1000 ends per parameter into warp count into text 1 plus warp crimp plus peaks per parameter web count in text plus 1 plus wet crimp. This is a very standard equation which you will find in many textbooks also. So, we are writing the same thing, fabric areal density like this. Then we are writing it in terms of EPM is changed to EPI, and therefore, a constant 39.4 is coming over here. The equation otherwise is same. Now, let us assume that the warp and weft contributes equally to the weight. That means, it is a fabric where warp density and weft densities are exactly same, and they are also made from the same yarn. Therefore, half the fabric weight is going to be how much? 39.4 by 1000 EPI WPTX and 1 plus C1. That is, the contribution made by the warp is this, same will be the contribution made by the weft also. So, this is a kind of balanced fabric where both warp and weft counts are same and ends and peak densities are same. So, half the fabric weight will be equal to this, equation number 5. Now, comes another important assumptions which is sometimes may not be possible to do also, that is what should be the crimp value, that value of C1. Now, crimp is always there in any woven fabric, but that is it is very difficult to really predict the crimp in advance. Crimp can be measured once the fabric is made. After that, we can easily find out what is the crimp in warp and weft. So, what we should do initially, we should assume that there is no crimp, crimp is 0 on both sides. If we do so, then half fabric weight becomes 39.4 by 1000 into EPI and WPTX, that is ends per inch into warp count in text. So, here we are assuming that there is no crimp, and based on that this assumption we are going to calculate. So, there was the first assumption which was the translation efficiency. Now, this is second assumptions, that is crimp is 0, and let us see, let us find out what sort of values we get. Now, if we have this, then we can write the fabric weight which was given 0.27 kg per meter square. So, we will convert it into gram and then divided by 2, this is the weight contributed by the warp yarns, and hence we write this equation. From there what we find out, that multiplication of EPI into and warp count is a value 3426.4, that is EPI into count of warp should be 3426. So, here also you see ultimately we are ending up with an equation where there are two unknowns and one value given. So, we have no way to find out. Theoretically there could be so many combination of EPI and W warp count to get this value 3426. There could be innumerable number of combinations which is possible, but all the combinations will not work because we have to meet other requirements also. So, what is the other specifications given here, that also we have to include. Okay. So, we will come to that. Now, if we write that strength is this, we have written it earlier, the equation number 1. Here the EPI and this value we have found out already, that is 3426. Now, if we apply this value here, then I am left with TWP, that is the strength of the warp yarn or tenacity of the warp yarn. From there we can find out what is the tenacity of the warp yarn, and that gives you a value 75.8 gram force per tex, which is in terms of denier it will be 8.425 gram force per denier. So, therefore, we could find out that this is the tenacity of the yarn that we need in order to get a strength which is 249.3 kg force per inch. So, at least one important parameter we could estimate. Here we need to just write few more points, just that is sometimes grab strength generally is greater than strip strength by 30 to 40%. These have been stated by some researchers that generally grab strength is more than strip strength by 30 to 40% for cover factor greater than 12, and for very open structure grab strength and strip strength are almost same, because sometimes grab strength may be specified and therefore, you want to convert then grab strength to strip strength to estimate the parameters. It is also influenced by the inter-yarn friction at crossover points. Thus, grab strength will decrease for whips with long floats, twill, basket, satin. This is just a general information which is stated here. So, therefore, yarn tenacity we could estimate right now. Next comes estimation of yarn linear density, which we have not been able to find out, and what is the end density, that is EPI, these two we have not been able to find out till now. Let us say fabric minimum thickness H fab is actually given by this equation by some authors, that is H fab gives d of warp plus d of weft multiplied by eta, where this value is 0.75 for combined cover factor greater than 20 and 0.60 for cover factor between 15 to 20. This is suitable for filament yarns where twist is very low. For low twisted filament yarn, this is what has been stated, and therefore, we make use of these equations and try to see whether we will be able to predict the yarn count and ends density. And what is this? This is compressed yarn diameter by original diameter of both of these are basically for the yarn. This value should be equal to 0.6. Now, fabric thickness therefore required is 0.5 mm that has been stated. Therefore, we can write 0.5 is summation of diameter of warp and weft multiplied by 0.6. If we assume that yarns are of same linear density yarn we are using, that is we are using the same count of yarn in both warp and weft, then diameter of warp yarn and diameter of weft yarn are exactly same, that is let us say diameter of yarn dy, and therefore, we will write that 0.5 is 2 dy into 0.6 and hence diameter of yarn is 0.416 millimeter. So, we are finding out the diameter of the yarn from the information given, which is the thickness of the fabric, and using the relationship that the fabric thickness its summation of diameter of warp and weft multiplied by a factor which could be either 0.6 or 0.75. So, we get some estimate of yarn diameter. Now, this estimate if we know the diameter, if we find out, now there is relationship between diameter and count. This is the relationship between diameter and count. This is there in many standard textbooks, where only thing which is unknown to us is now density of the yarn. What is going to be the density of the yarn? Now, it all depends on the packing value. Yarn density is fiber density into packing factor. The packing factor chosen here is around 0.6, which is also typical packing factor for the based on the classical formula of Pierce we are using here, which gives a value of 0.6 the packing coefficient. Now, if you use that value, then what we get ultimately the diameter of the yarn is this. From there we can say that diameter is root over c x count of yarn 3.921 into the power minus 2. So, if this gives you the value like this, diameter of the yarn is 0.0392 root over warp count in text. Now, here if we substitute the value of diameter of the yarn which you have found out earlier, then we can find out what is the count of yarn in text, and this gives a figure which is 113, 112.6. So, we can choose a value either 112 or 113, that is going to be the yarn count. And if this is the yarn count, then the ends per inch is going to be 3.3426.4 or 3426 divided by count of the warp yarn. Exact values are this, we can take the ratio of these two and it gives a value around 30, or ends per centimeter is going to be around 12. Therefore, we can find out now what is the count of warp that we are going to choose and what should be the ends per centimeter or ends per inch or ends per meter, whatever it is. So, based on certain assumptions, we are in a position to estimate certain parameters, and these are initial estimate, they are not the final estimate. Now, with these estimates we can think of then making a fabric and study that is it meeting the requirement of strength and GSM or not. If not, we have to then start modifying these parameters. So, initial estimations can be done following this methodology. So, estimated parameters are warp count is this, same is going to be the weft count, tenacity is going to be the 8.4 gram per denier, and EPI, PPI going to be 30. With this, now we have to think whether I can get a yarn exactly of this text. If we do not find a yarn which is available, suppose with us, or commercially exactly 113 is not available, then any text closer to this value we have to finally choose. Suppose 113 is not available, but 115 is available, or maybe 98 is available, or just 100 is available. This kind of practical situations may be there, then we need to adjust. So, whatever is available closest to these values, we have to choose that yarn from our inventory and then recalculate that if I use the yarn which is available, which is closer to this, will it meet the requirement of strength in both the directions, warp and weft, and whether it is going to meet the GSM requirement and the thickness requirement or not. Okay. The other method of finding out the yarn count is also stated here. Now, we all know this is very common that yarns within the fabric assumes elliptical cross sections due to contact pressures. Area of an ellipse is pi 4 a b, where a is the major axis, b is the minor axis. You all know that. So, we are assuming that each and every yarn is actually elliptical within the fabric. Now, one important paper which I have found out that this ellipticity has been quoted to be, that is B by A ratio minor by major axis varies between 0.3 to 0.8 for weft yarns and 0.3 to 0.62 for warp yarn. This is available with this particular paper. Here they have taken the filament yarns, twisted them to different levels, woven them with same ends and peaks per inch, and then they have cut the cross section of the fabric, and then they have measured the both minor and major axis, and based on that informations we can see that the weft yarns ellipticity values varies between 0.3 to 0.8 depending upon what is the twist in it and what is the corresponding twist in the warp yarn. So, because it is interaction between warp and weft, every interlacement point is a source of pressure, and under that pressure the yarns are going to flatten and is going to take a elliptical shape. So, if there is no elliptical shape, the B by A value is going to be 1. If there is no change in shape, the yarn remains round even within the fabric, then we can say the ratio of B by A is going to be 1. So, 1 basically means the yarns are round in shape within the fabric, and the lesser the value means more elliptical it is. So, this is the range in which the B by A values are going to lie. So, this is the ellipticity ratios which are shown by the same authors. I am just going to show you. This is weft and warp directions. The vertical chimneys are basically indicating the warp ellipticity, and here it is weft ellipticity. So, weft ellipticity values can go very high, 0.8. The warp ellipticity value maximum is going up to 0.6. So, weft becomes deformed more and more in this particular example than the warp yarns. And why? Because warp yarns are under more stress always, they are under tension. So, possibilities of deformation of the weft yarns are more. Okay. Now, let us go to this now. What is the yarn density? We have to find out now. Now, this value we have calculated actually from the data offered by these previous authors. If we actually note down the minor axis and major axis values of the filament yarns from the data that the authors have suggested, we could found that the phi is actually varies between 0.8 to 0.9 within the fabric. Phi values, packing of phi values varies between 0.8 to 0.9. 0.9 is the maximum, is a closed pack geometry of circular fibers. We can get a value of 0.9, otherwise it will be 0.8. It is all within the fabric. You have to remember, this is not outside the fabric. Within the fabric, the yarns are locked in positions and there are pressures, therefore, they are highly compact. So, packing coefficient is very high. These are filament yarns. For spun yarns, packing coefficient cannot be 0.8, it will be much less. So, anyway, we are choosing a value in between, which is 0.85. If we choose a value 0.85, then the yarn density becomes how much? 1.38 into 0.85, that is 1.17 gram per centimeter cube. That is the density of the yarn. Now, if this is the density of the yarn, then the compressed yarn diameter within the fabric is going to be the minor axis, that is the B. In this diagram, this is the compressed diameter. So, that is going to decide the overall thickness of the fabric. So, fabric thickness given is 0.5 mm and H fab varies between 2B to 3B. We have chosen similarly in this case also 2.5B. So, we are considering the deformed shape of the yarn, where the minor axis of the ellipse is actually considered to be the diameter of the yarn. So, from there we can find out what is the value of B. So, B value is coming to be 0.2 mm or 0.02 centimeter. Now, based on the definition of yarn count expressed in text, we can write this pi 4 AB, because it is the ellipse now within the fabric. So, pi by 4 into AB in 10 to the power 5 into rho y is going to be the text value of the yarn, this count of yarn in text. Therefore, pi by 4 into B and this is another value we have chosen 3b, that is A is equal to 3b. Why? B by A in the case of very low twisted yarn, we have seen that B by A value is usually 0.33, that is A is 3 times than B, it gets deformed so much. If we look back the elasticity values, then we will see that when the yarn is twist is 0 or the lowest, when it is going to deform maximum, there this is the value we usually get, and therefore, A has been replaced by 3b in this case, because we are going to form a liner from filament yarn which are hardly twisted or very low twist is there. So, maximum deformation is going to take place. With this, what we can write, that B square into 2.756 into 10 to the power 5 is C tex, and therefore, tex value of the yarn is going to be this much, that gives you a value 110 tex. And if this is the value of yarn count, the yarn ends per inch is going to be 31. So, if you compare this yarn count, yarn tex, yarn count and yarn, so the ends per inch with the previous method, they are very close to each other. So, either we follow this method or that method, we end up with a count which is very close to each other, and this is true for fabrics made from filament yarns, that too from low twisted filament yarns. So, that lot of deformation happens within the fabric, and fabrics which are to be coated, these fabrics now which will be acting as a your swimming pool liner, they are all coated fabrics. So, after we make the fabric is coated to protect it from especially sunlight, protect it from abrasions. So, there are many reasons why we give a coating to the fabric surface, and if we want to give a coating to the fabric surface has to be very, very smooth. The ups and downs on the surface of the fabric is not good for coating applications. If we want to have the surface very smooth, at the same time we want a stable constructions, then low twisted filament yarn and a plain weave is very, very suitable, because if the yarns are low twisted, they will be deformed, and the thickness of the fabric is going to be very low also, because both warp and weft yarns are going to get compressed and going to get spread out. So, the entire yarn distances is going to be all covered. You will not be able to see much gap between them, because the yarns are going to spread out, they are going to take a elliptical shape, both warp and weft. So, that is why we generally prefer low twisted yarns, filament yarns in such applications. So, we see here a comparison, method A gives you these values, method B gives you these values. So, they are very close to each other, the values are. And if we see, suppose in our inventory these yarns are available, yarn available at denier wise these, therefore, we can see out of this in terms of text 111 is close to whatever values we have found out. So, these yarn can be chosen from text count point of view, and now we also need to know what is the corresponding tenacity of the yarns, because this yarn if we choose, it must meet the tenacity requirement which is at least 8.4. If it is more than 8.4, it is still fine, but we cannot choose a yarn whose tenacity is less than 8.4. Okay. So, from there this is what I think is all about. The other important point that may come is selection of the weave. As I said, we are going to choose the plain weave because it gives you the firmest structure due to maximum number of interlacements. So, for such applications this kind of structure is suitable, and plain weave is easy to manufacture also. Choice of other type of weave which you may be familiar with, that will depend upon what sort of tear strength we need, or bending and shear rigidity, or permeability values, or abrasion resistance. So, different construction gives you different type of tear strength from the same yarn, or bending and shear rigidity may also change if we change the constructional parameter or the design of the weave. That is, if we switch from plain weave to twill, or twill to sateen, or different types of twill that we have, or basket weave, these are the properties of the fabric which is going to change. So, whether we will go from plain to basket or plain to twill or not, that depends upon now whether what sort of requirements are there from the point of view of tear strength, bending rigidity, permeability, abrasion resistance, etc. We have earlier discussed the estimation of design parameters for technical fabrics. So, this is another example of the design. Let us say we have to estimate the design parameter of a fabric to be made from rotor spun yarns. All right. So, the yarn has been specified. The designer need not to find out which yarn he has to choose, whether ring yarn, rotor yarn, combed yarn. So, that is not important now. It has been specified that let us say the yarn to be chosen is rotor spun. The specifications that we have to meet, this is the technical requirements. What are the specifications? The aerial density should be 252 gram per meter square. This is the GSM of the fabric. The other thing is thickness. Fabric should have a thickness of 0.6 mm. So, thickness has to be 0.6 mm. Warp end density should be twice of weft yarn density. So, whatever is the weft yarn density, warp density should be twice of that, or vice versa. If the warp yarn density is x, it should the weft yarn density should be x by 2. And warp yarn count is 60% of weft yarn count. So, this is the specification given, and let us say you are asked to give or estimate the various design parameters, so that the person, the weaver, can produce the fabric. So, how to go about it now? Let the weft count be C2. So, therefore, the warp count is going to be 60% of it, 0.6 into C2. Weft yarn diameter is D2 and warp yarn diameter is D1. We are not sure what is the diameters of the two yarns. We do not know what is the count also. But we know that dy is proportional to root over count. Count is expressed in Tex units. So, dy is proportional to root over C in Tex. Therefore, d1 by d2 is going to be C1 by C2, that is 0.6 C2 by C2, and hence it is going to be root over 0.x, that is 0.774, and As a result, diameter d1 is going to be 0.774 d2. So, warp yarn diameter will be 0.77 times the diameter of weft yarns. Now, the fabric thickness has been specified. So, we have to meet this requirement. Now, fabric thickness is, if we look at back some of the textbook if we refer, we will find that T minimum and T maximum, these two values have been shown to be, T minimum is d1 plus d2 and therefore, it is going to be 1.77 d2. We put the value of d1 in terms of d2 and we get it 1.77 d2. And the maximum fabric thickness as shown it here, T max is going to be d1 plus d2 plus d1. So, it will be 2 into 0.7746 d2 plus d2 is close to 2.55 d2. So, minimum and maximum thickness are related to the diameters of warp and weft yarns, and we see that means the thickness is going to lie between 1.77 d2 to 2.55 d2, somewhere between these two. Let us assume a mid value of thickness to start with, because we do not know how much is going to be the compression, what is going to be the final exact thickness value of the yarns, because after the fabric is woven the yarns get compressed and they take mostly elliptical shape, and based on that the thickness is decided. But we know the two limits, upper limit and lower limit, and let us assume it as an initial estimation that it is in between these two. So, it is half of this, which is 2.16 d2. So, if the fabric thickness is given 0.6 mm, hence 0.6 is going to be 2.16 d2, and therefore, the value of d2 we can work it out, that we have to produce or to get a yarn whose diameter is going to be T fabric, thickness of fabric divided by 2.16 is going to be 2.77 mm, 0.277 mm. That is should be the diameter of the yarn. Now, diameter has to be then translated to count, because we need to know what is the count that the person is going to use. Ultimately, we have to find out the count value. So, if we have seen that this is a typical relationship which is available in the textbooks, that pi d y squared by 4 into 10 to the power 5 into rho y is count value of the yarn C tex, and yarn density is fiber density into yarn porosity. Therefore, the diameter of the yarn is root over 4 C tex by pi into 10 to the power 5 into rho y. Yarn porosity within the fabric ranges between 0.55 to 0.75. This is also an important information, and this needs to be found out from some research article, because unless we know this we will not be able to really move ahead. So, we have to find out, dig out some informations from the literature review, or if it is not at all available, then we need to do some research, in-house research, to find out these values. So, yarn porosity, it has been shown to lie between within the fabric, it varies between 0.55 to 0.75. So, the yarn density is going to be 1.50, if it is cotton yarn, fiber density is 1.5, and then we have taken a value 0.6 is the typical value of porosity for rotor yarn. So, we have chosen a value of 0.6 for rotor yarn. So, with this assumption 0.6, we have to move ahead, and if we know the density of the yarn, then we can find out what should be the diameter of the value d 2, because d 2 is going to be from the formula straight away right. We substitute all the values that we have, and we will find out that the d 2 is going to be root over C 2 3.76 into 10 to the power minus 2. From there, we can find out what is root over C 2. It is going to be 7.3 root over C 2, because d 2 we have already calculated, which is 0.277, and therefore, C 2 is going to be 7.3 square, that is 53.29, that is close to 53 tex, and C 1 is going to be 60% of it. So, C 1 is going to be 32 tex close to. So, this approach can give us the what are the values of count of the two yarns that we have to use based on certain assumptions. And the assumptions, this is not a random assumption, assumptions are based on certain research article. From there, we have to not only find out the count of yarn, to make a fabric we need to know what should be the ends and picks per inch as well. So, first assumption is, let us assume the 0 crimp fabric, that the fabric has no crimp, which is practical sense it is not possible, but to start with we will make assumption that it is a 0 crimp fabric. So, weight contribution by warp and weft therefore, will be same, provided the counts are same. So, aerial density of the fabric is given 252 gram per meter square. So, weight contribution by warp yarns is going to be 126 gram, and therefore, N 1 into C 1 by 1000 is going to be 126. From there, we can calculate what is the web density N 1, which will give you a figure 24 per centimeter. And if we go further, N 2 we can calculate again, and we get a figure 39 per centimeter. From there, if we go to the next assumption, then let us assume a 6% crimp. Typically, in a cotton fabric, that crimp in both warp and weft can vary a lot, and it is very difficult to know in advance what is going to be the crimp in the fabric. But based on lot of the articles which have been published, there are varieties of data which are available, and we have taken an estimation, a typical value which is, let us say, 6% of crimp is there in both warp and weft. In that case, and weight contribution of both warp and weft are same. So, these two are my assumptions, and with this assumption if we go, we can write W by 2 GSM divided by 2 is 1 upon 1000 N 2 C 2 1 plus small c 2 by 100, or small c 2 indicates the crimp value and capital C 2 is the text value of the yarn. So, in this if we go by this, we can find out what is the value of N 2. So, we solve this and find out the value of N 2, which is 22 per centimeter, and the same procedure we adapt to find out the value of N 1, the warp end density is going to be 37 per centimeter. And with these two, if we move ahead, then we will find that in this table actually actual values are stated in the very first row, fabric cotton, thickness is given here, weight given, fractional cover also given, diameter of the warp and weft are given, thread density, warp and weft, linear density of the two yarns, warp and weft are all stated here. So, these are the actual values which have been used to make this fabric, and the calculation that we have made on the two assumptions, no crimp and 6% crimp, the corresponding values of especially thread density and linear density, these two are what we require in order to produce the fabric. We find the values with no crimp assumptions, the values are coming 53, 32, 24, 39, thread density 39, 24. And if we compare to the actual is 44, we get a value 39 here, 23, we get a value 24, they are very close, 30, 32, 49, 53. And if we go by the 6% crimp, then the figure is going to be how much? That these two is not going to change, the thread density is changing from 23 to 22, 24 earlier it was 24, it has become 22, it was 39, it has become 37. So, actual values are 44, we get 37, we get 23, we get 22. So, we arrive at a values which are reasonably close to actuals. That means, if we take a procedure like this based on certain assumptions, we will be arriving at values which will be relatively or quite close, not exact values to the actuals. So, obviously, for a designer, based on these estimate, he has to actually produce a fabric and again go for checking. As we make a prototype, that is why you say that first is the prototype. So, you make a prototype or you make any based on your initial estimates, you actually make a fabric and then check whether it is meeting the requirements or not. If it is not meeting requirements, now you have to basically play with the parameters. Some parameters have to be increased or something has to be decreased, so as to make sure that it meets your specifications. So, these are basically the initial estimates and not really the final one. So, with that we close this particular discussion on this particular example, and similar logic can be followed, but we know that there are certain difficulties are there, like crimp is itself is very very difficult to assume. So, based on lot of data collections, one can only assume that if I make a fabric on this loom from this type of yarn, this is the typical crimp value that we get. So, that data bank should be available with the designer also, so that he can make a very careful choice of the some parameters, not an arbitrary selection of parameters. Okay, thank you.